Hello, we are starting our next unit, Unit 10, talking about probability distributions. So this is taking what we know about probability, so this like kind of basic level of probability, and taking our basic level of statistics and bringing them together to bring both of our ideas of probability and statistics up to the next level. So this is where things are going to get a lot more complicated. So definitely feel free to start asking questions a lot more. Because this can get really tough. I'm going to try and break it down in ways that are easy to handle, easy to munch on, easy to digest. But if I don't succeed, definitely it's up to you. You've got to make sure you're asking me questions so I can help you out. So first, in order to just entry our way back into here, we talk a lot about random discrete variables, discrete random variables. And so just to remind you about what's discrete versus continuous. So I want you to go ahead and take a stab at all 6 of these variables. D is a little bit tricky, so keep that in mind. And I want you to tell me what types of variables these are, discrete or continuous. Remember that discrete is something that's countable versus continuous is something that's measurable. Okay, here are the answers. The number of hairs on a Scottish Terrier, the number is a great hint to you that this is discrete. Another way to think about this is you can't really count half of a hair of a Scottish Terrier. So this would be just discrete. The height of a building is a measurement, which means that this is continuous. You could have a building that's 1.3427 something meters tall. And so you can continue going deep within the number line in order to find that measurement, which means that it's continuous on the number line. The amount of fat on a steak is something that's measured. So that would be continuous. We'll save D for last. E, the number of fish in the Atlantic Ocean. Again, the number is a hint to you that this should be discrete. And then the temperature of an electric kettle, this is continuous because it's measured. Its temperature is measured. A high school student's grade on a math test. Your textbook says that this is discrete because that there are specific values that are associated with, even though your values can get smaller and smaller and smaller, there are like specific values that are associated with those numbers. And so they're saying because it's A, B, C, or D, it values it under discrete. I would say it's debatable. I would say it's debatable whether it's discrete versus continuous. So your textbook said that it's discrete. I would say specifically because it says a grade, not a percentage. And so if it says percentage, that would technically be more continuous. A grade, I'm assuming what they mean here is like A, B, C, or D, or whatever that equivalent is in different countries. And so that is why they think that this is discrete. That one was tricky. I don't blame you if you got it wrong. Okay, really quick refresher. I'm trying to keep it quick because we've got a lot of graphing stuff to do today, and I know that that can tend to stay longer, so just try and move past. Just a quick refresher on what discrete versus continuous is. It just kind of like continues to pop up every once in a while, so I just want to make sure that you were refreshed on that. So we surveyed a bunch of people about the number of phones that they have, and then this is the frequency of the number of phones that they have. I would like for you to go ahead and calculate the relative frequency. Can you tell me really quickly, choose from the list below, how do you calculate relative frequency? Remember that this word relative refers back to this idea of referring to something. The fall time, autumn, is cold relative to the summer, but autumn is hot relative to the winter, right? We're relating it back to something else, and that thing that we're relating it back to is the whole. So what we do in order to find relative frequency is we divide each of these frequencies by the total number of frequencies that we have. So first we have to add all of these guys up, which is 200. And then now we're going to take each of these frequencies and divide them by the total. So we're going to do 3 divided by 200, and that is 0.015. We're going to do 47 divided by 200, and that equals 0.235. Because we've got a lot going on today, I won't ask you to calculate these out individually. because I want to make sure to make the best use of your time. You know how to divide, you know how to write decimals. So there are your relative frequencies. And the reason why we're talking about relative frequencies, hopefully now that we've circled back along to probability, is this is the probability of that number popping up if you randomly selected somebody, right? If you randomly selected somebody from the 200 that you interviewed and said, what's the probability that they have 0 phones? The probability is 0.015, right? Or 3 over 200. So this is really relative frequency that we learned at the very beginning of the year is really just the probability, which a lot of you guys figured out. It's really just the frequency of, the probability of you having that number if you pulled randomly from the pool. So when we talk about the probability mass function, now we're going to see something that looks like this. And it's the probability uppercase X is the thing that you pulled, right? If we've got a pool of 200 people, uppercase X is the person that you pulled out. So the probability that the person you pulled out is equal to, and then lowercase x is this value. This is X equals 0, X equals 1, X equals 2, X equals 3, X equals 4, all lowercase. So the probability that the thing that you pulled is 0. And that is 0.015. The probability mass function P of X equals 0, or P of uppercase X equals 0, is just your relative frequency. It's just the probability that this was pulled. Very simple, but a very weird notation. I'm sure you all noticed in previous tests the weird function notation that goes along with probability in some of your later formulas. And this is us first starting to understand what that notation stands for. And just the probability that you pulled this number from this value from the people that you pulled out of the crowd. So you should write somewhere on here the probability of observing this outcome. So the probability of observing somebody that has 0 phones is 0.15%, or sorry, 1.5%. Okay, so we can take all of this and we can turn it into a frequency graph is what they call it. It's really a histogram. So I'm going to grab a ruler and a pen. We are drawing a histogram, so remember that our histograms have our y-axis all the way to the side, x-axis all the way at the bottom. We need to make sure to label our axes with a title, with words, as well as with numbers, creating a scale. So if you go every 3, put a tick mark. I'll just tell you what the scale is. I knew that I had 15 boxes and I had 5 numbers to represent. So I took 15 divided by 5 and I knew that every one was going to be 3. So that's going to be 0, 1, 2, 3, 4. In the center, because this is a histogram, so remember we're going to draw little bars that represent each of these values. And then I need to make sure, so this is number of phones. And then I need to make sure that I label my probability over here, and I'll have I think it'll just be probability and not like percentage, which I could put it as a percentage. I just had to, well, I almost wrote percentage. Probability. So as long as you label it probability, then you have to give numbers that are probabilities. Okay, our largest probability is 0.425. I think it's 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I've got 12 boxes here, and I need to go all the way up to, in my head, I'm thinking 43. So 43 divided by 12, the closest thing I'm going to get to here is 4. 4 times 12 is 48, versus if I did 5 times 12, that would be 60, which would be too much. So I'm going to go by every 4. which means I'm going to use every single tick mark. So that's going to be 4, 8, 0.04, 0.08, 0.12, 0.16, 0.20, 0.24, 0.28, 0.32. You get it. Not my prettiest looking graph, but we'll take it. Okay, probability that a 0 came up is 0.015. So 0.015 is going to be way down here. And we're going to draw it like this. Teeny tiny little bar. The probability that a person has one phone is a 0.235 probability. So that 0.235 goes all the way up to almost 0.24. So I'm going to go ahead and put a line just under 0.234. I should be using my ruler for this. Probability of pulling out 2 is 0.425, which is slightly more than halfway between 0.4 and 0.44. Yes, you should be drawing this. Yes, I will check it in class. I bet I caught one of you not drawing it. 3 phones would be 0.245, which would be slightly above 0.24. Takes time. But now you need to know where these come from, that they represent frequency divided by total, that they're representing the probability that a 2 will show up, that people own 2 phones will show up highly versus 0 is really low, 1 is like a fourth of the people, sorry, not even a fourth. Yeah, a fourth of the people that you pulled have 1 phone, slightly under half have 2 phones, and then a fourth have 3 phones, right? So you need to understand where these visuals are coming from and why they showed up and how they're made. A lot of times, like at the very beginning of our probability unit and our first probability unit, our first statistics unit, we spent a lot of time graphing, a lot of time creating frequency charts and frequency tables. And it took a really long time to go through and count. And the reason was because I wanted you to know what it actually means to have a frequency part of your diagram. The fact that 0 showed up 3 times, 1 showed up 47 times. Somebody sat there and counted the number 1 47 times. So that way you know that frequency is crucial in telling us what's going on with these data. If you forego the frequency, you don't have any information. These are just labels, right? They're not real numbers. And a lot of you guys are trying to do calculations without the frequency, and that's there is no math without the frequency. So please just remember that these processes and doing these processes are trying to solidify something in your brain about how this works so there isn't misunderstandings later on. So understanding if this is easy, like this idea of making this table, this histogram is really easy, good. Remember though that what it stands for this probability that a 2 came out, which meant 2 came out much more than any of the other numbers. It represented 4 to 42.5% of all of your frequencies. So keep it in mind. It'll come back later, and I need you to make sure that you understand how to read this. So now I need you to be able to understand